It's funny because engineers say exactly the same. You know, being a lot of engineers, we are not responsible for what physicists do. I don't know how popular are this type of things between the people here, physicists and engineers. Seems that in Latin America we are more relaxed for this sort of thing. Nobody's offensive. I know the culture here perhaps is different. Perhaps in Italy probably they understand. Right? What happens in the northern country?
Yeah, it's slightly different. And I mean here, Austria is quite focused on titles and so on. So that will be maybe a bit different. Okay, I think we need to kick off. It's 4 o'clock. Good afternoon, everyone. I welcome you to the session on topic 3.2, radionuclide technologies and applications. We have 3 presentations today, and our time is limited to 55 minutes. And with this, I'll hand over to my dear colleague, Ricardo.
Okay. Presentation will be done by Dr. Michael Foxe from PNNL. Impact on nuclear detector technologies on Radioxenon laboratory operation. Mr. Foxe, please.
Thank you. So as was mentioned, I'm Michael Foxe from Pacific Northwest National Lab, and we've heard a lot about different detector technologies over the course of this week, and we will hear more. But I'll talk a little bit about not necessarily their impact for the stations, but how they might impact radionuclide laboratories. So I'll go through, first to start, the kind of current IMS systems and what they look like and how they might compare to the radionuclide laboratories as we operate them now. And then I'll go through some of the new generation of the IMS systems, what type of changes have been implemented, and how those kind of are being incorporated or may be incorporated into the radionuclide laboratories. And I'll go through the nuclear beta cell, kind of what the resolution looks like and what that impact is for the radionuclide laboratories, and then the kind of operational scenario and what I see as the overall impact for future. So the current IMS systems there's kind of 2 methods of detection, either beta-gamma detection with a plastic scintillator and a sodium iodide for the beta and the gamma detection. So you can see here kind of on the left-hand side of the SANA system with the detector highlighted there, or hypergermanium gamma spectroscopy with the SPOLX. And both of these systems go through and do a whole lot of chemistry that happens in the field so they can measure that sample right away. And that's one of the key differences that I'll highlight moving forward is that sample gets measured right off the bat as opposed to being archived and shipped to a laboratory for future measurement. So if we start to then look at some of the new generation of the accepted IMS systems, there's either still beta-gamma detection with sodium iodides and plastic scintillators for the gamma and beta respectively, or there's also now beta-gamma detection with a silicon beta cell and hypergermanium gamma detector. So on the bottom here, you can see the 3 different systems of the SANA 3 and Z International, which are using the plastic scintillator and sodium iodide. And then on the right-hand side, the SPOLX NG, looking at the PIPS box, which is a silicon beta cell, and hypergermanium detector. So if we go to the next slide here, I'll dive in to what type of signals we see from these detectors in a little bit more detail. So on the left-hand side, I show an outline of kind of the beta-gamma detector for the SANA 3, as well as or for the SANA detector, as well as the beta-gamma detector for Z International, where there's a slight difference in terms of how many PMTs are used and kind of where they're situated, but they both operate the same, with the same mentality of plastic. The gas goes into the beta cell, and so that's one of the key things is gas goes inside the light collection, and so it gets 4-pi collection of that signal, and then the gamma escapes that plastic cylinder beta cell and is detected in that sodium iodide. And so you can see in the spectrum here with the beta signal plotted on the x-axis and the gamma signal plotted on the y-axis. And we can see the different regions of interest kind of as we see with the 133 signal and 133M there from the Radioxenon signals. And then if we look at the right-hand side, there is highlighted the PIPS box, which you can see on the two right-hand pictures of where the gas goes in, and the gas is kind of sandwiched between two silicon detectors. And as that beta interacts with that silicon, it's detected, and then the gamma transitions out and is detected with the high-purity germanium. One of the key differences you might see here is there is not 100%, it's not 4-pi collection for that silicon beta cell, and that's just because of things like, because the mechanism for detecting the beta is not the same as the enclosure for the gas. And so that's one of the key differences for impacting that dead volume. And you also see the PIPS box sits on top there of the Beji detector, and so there is kind of 2-pi detection for the gamma detector as opposed to nearly 4-pi for the sodium iodide. And so those are two things I'll highlight for the laboratory scenario as we move forward. I mentioned two different detector mechanisms for the detection of either plastic scintillator and sodium iodide. There's also other scenarios where we might run into it of low resolution sodium iodide with kind of a higher resolution for the beta cell, so silicon. We can take that PIPS box tile detector, different form factor maybe, and put it inside the housing of the sodium iodide, and we can have the beta gamma there with high energy resolution for the beta and low energy resolution for the gamma. Alternatively, there's the option of taking that plastic scintillator beta cell and maybe put it inside of a hypergermanium well and having low energy resolution on the beta and higher energy resolution on the gamma detector. So those are kind of the 4 different scenarios where we might be able to further leverage that detection mechanism and implement it for a laboratory compared to a IMS station. So you can see here on the 2 different mechanisms, primary setups that I'm going to be focusing on for the rest of this kind of study is the standard, what we're seeing here for the SnT detector and the Xenon International, where it's plastic scintillator beta cell and sodium iodide, so it's kind of low resolution on both, and using those regions of interest to identify each of the radioxenons, as well as the scenario where we replace that plastic scintillator with a silicon beta cell. So same regions for the gamma detector, but then also shortening up that those regions for the betas by having that improved energy resolution. So if we're looking at the beta cell resolution, there's a few key differences that I'll kind of talk through on this slide here as we look at the comparison. So we have the plastic scintillator on the left-hand side and the silicon beta cell on the right-hand side. One of the first key things that may jump out to you is looking at the 2D spectrum on the right-hand side. That dot from the 133M is much more defined compared to the dot on the left-hand side for the plastic scintillator. If we're then also looking at that 2D spectrum, one of the things that you might notice is the threshold for the beta cell is slightly higher than that of the plastic scintillator. So the events on the left-hand side don't go all the way down to 0. And so with that, it's going to be reducing some of that efficiency because we're not going to detect all of those betas from the 133. If we go down to the bottom plots now, we can look at, I mentioned the energy resolution, but you can really see where that impacts the detection efficiency as well as kind of the minimum detectable activity. So the interference from the 133 spectrum and continuum on the both plots, you can see it there, but then there's kind of a hump from the 133 on the left-hand side versus sharp peaks from the 133M on the right-hand side. And so not only that, but you also have 2 peaks that are present from both conversion electrons in the beta singles that pop out as opposed to a skewed Gaussian. So these are kind of leading to opportunities where we may be able to further reduce our interferences from the 133 when we have either 131M or 133M, and being able to improve our detection long-term if we're just focusing on those metastable isotopes. So talking through what we expect for the operational scenario of the radionuclide laboratory. So I've talked through the different detectors. Now I want to see, okay, what types of samples are we expecting to get? What needs to be the focus of those detectors? So there's a few different sample types that we generally get at a laboratory. So there's either kind of QA/QC radioxenon spikes, where a spike of radioxenon will go to a station, be injected into the station, and then sent back to the laboratory. Those generally most of the times, those include xenon 133 and 131M, as well as sometimes 133M. But the primary two isotopes we're going to be seeing with those are the 133 and the 131M. And since it's a spike at the station, they're generally higher activity as well. And so there's not a huge drive on those samples to make sure we have the lowest sensitivity possible for that xenon 131M, because we're able to pick it out at the higher activity. I mentioned proficiency test samples, where there is the expectation that we're going to be mimicking either the QA/QC samples or potentially an environmental sample, which I'll go through in a second here. But the wide range of proficiency test samples, we don't know exactly what we're going to be getting because it's a blind test. But we want to be able to make sure we're capable of sufficiently measuring all those different isotopes and measuring low levels, because they may be in there at a low activity. And environmental samples can be kind of a range, but generally as we start to measure the environmental samples, they're going to be lower activities, because it might be close to the MDA of the IMS system, which means it's probably close to the MDA of the laboratory, but that's one of the areas where we might want to focus on improving the MDA so we have that additional measurement. So I mentioned the shipping timeline here, 7 to 15 days, usually between when it's collected and shipped to the laboratory, which means we're not going to be seeing that xenon 135 or the 133M usually. But if we are in a scenario where we see all four isotopes, then the same goals of that detector is going to apply for both the IMS station as well as the laboratory, is trying to make sure we can see all of them with that interference of everything. So a few things that can impact the radionuclide laboratory kind of for that detector is optimal counting time depends on the detector background for the detector. So if we are picking a material like silicon with high resolution compared to the plastic scintillator, just the background in general we want to make sure is low, but also the interferences as we start to see 133 interfering with the 131M. And we may also be able to optimize our counting durations to focus on a specific isotope. We may count for a short amount of time for the 133 and then a longer amount of time for the 131M, and it doesn't have to necessarily be a standard operation. I will mention that I show here the less than 4 pi geometric efficiency for the silicon is one of the things that will drive us to have a slightly worse MDA for the higher resolution silicon compared to these plastic scintillator. Interferences and gain stability. So the interferences I mentioned with the improved energy resolution, it makes it much more, makes it much easier to pick out that 131M from the 133 background, and then without necessarily waiting for that 133 to decay away before we can make that xenon 131M measurement. And gain stability, both plastic scintillator and silicon are stable. They've proved stable in multiple systems, multiple different detectors over the course of the measurement time. But a still energy check is useful before and after the measurement so that we can ensure that our energy is where we expect it. So a few final conclusions I'll make based off of kind of what we see from the impact of these different detector types. We see plastic scintillator appears better for the 133 than the silicon, and that's driven by the 4 pi detection efficiency. Silicon outperforms the plastic scintillator if we're looking at 131M for the detection efficiency, with the caveat that that does require that we want to make sure we have sufficiently high detector coverage for that 131M. Shipping delays are going to mean what we want to make sure we have as the best sensitivity possible for 131M because it's so important for a laboratory operation. And I've mentioned the kind of different detectors may be useful for different scenarios, and there's nothing that requires a laboratory have just one single type of detector. So it may be something we want to look at in the future, is multiple different types of detectors based off of the sample we're getting in at the laboratory. And with that, I'll take any questions you may have. Thank you.
There's any question? Okay, if there's no question, let's go to thank you. To the following presentation. It's a next generation beta gamma coincidence detector with increased capability. Will be done by Mr. Dr. James Early from PNNL.
To use my slides, James.
So while we're waiting, I'll introduce myself. I'm James Ely from Pacific Northwest National Lab, and this work is a collaboration with a lot of people from PNNL. Many of them are who are in the room today. And I'll be talking about some next generation beta gamma coincidence that we're working on. And Michael has given us a nice introduction on a lot of the stuff that I'll be talking about, so can go through some of these slides fairly quickly, I guess. So as we know, radioxenon is important for nuclear explosion monitoring. It's a noble gas, and so it can escape from underground very easily and not interact. And the half-lives of 4 of the radioxenons are appropriate for long-distance measurements. And so it's a really great gas to be able to use for monitoring. And it decays. All of these decay either by a beta decay or a decay where they produce an electron, a conversion electron, or a photon, either a gamma ray or an X-ray. And so we can do beta gamma coincidence, or electron photon more appropriately coincidence, which helps to reduce the background. And so on the top plot here in blue, we have a gamma spectra, just a gamma single spectra, and then below that is, in the red, is a beta gated gamma spectrum. And you can see from the bottom plot, which is a ratio of the two, that we have a decrease in our background of a factor of 100 to almost 1,000 in some cases. So this really lowers our minimal detectable activity by a factor of 10 or more. And so this really helps, especially for field systems, because then we don't have to shield as much. So it's a really powerful technique, and as Michael mentioned before, a lot of the systems have now, I think all of the systems have now gone to beta gamma for their systems. Michael mentioned this. I'll just go quickly through this. This is an example of a beta gamma detector that is P&L design, and it's a plastic beta scintillator, which is a cell that holds the radioxenon. And it's a very thin cell, so it collects the betas and measures them, or the electrons, but allows the X-rays and the gamma rays to go through into the sodium iodide, which is surrounding the beta cell. The sodium iodide is a well detector in this case, and so provides good geometric coverage. There are some challenges, and mainly in the plastic beta scintillator. There's two of them. One is that the scintillator doesn't have very good resolution, and so a lot of the response is smeared out, especially for the metastables with the conversion electrons. The other issue with the plastic scintillator is what we call a memory effect. So the plastic absorbs xenon, and you can have crossover from one sample to the next sample, and it causes an interference from one sample to the next. This has been looked at for a number of years and is pretty well mitigated with an aluminum oxide coating now. There's still research that is ongoing in this problem. For example, at the University of Michigan, they're looking at glass scintillators, which won't absorb xenon. Michael mentioned this a little bit, but there's been a lot of work in electron detectors, and so the Spalex had designed and developed what they call this PIPS box, which is a nice form factor for silicon, and they combine that with high purity germanium, which gives us the best resolution for both the beta and the gamma. And then Michael mentioned the silicon detector that we're developing at PNNL, which is also a nice form factor. There are a lot of examples. I've just pulled another one where people are looking at silicon and different types of gamma detectors. This is from the Oregon State University, where they took a PIPS box and are combining that with a CZT detector, which provides a nice form factor for field applications, so you don't have the cooling that's required for the high purity germanium. And silicon provides better resolution, but as Michael mentioned, there's a couple of challenges with it, and one of them is this low energy noise that we have. And it comes about mostly from the capacitance in the silicon, and the larger you make your silicon detector, the more capacitance you have, and the higher the noise, and so you have to cut that off, and so you have this low energy resolution, or low energy cutoff problem. And in the top plot there, you can see with the 133 photon electron plot, so the gamma beta plot, we have a cutoff of about 40 keV or so in the beta spectrum. And so you lose efficiency and you don't gain some of the data that is at the low energies. The other challenge is that the silicon is a higher Z material than the plastic scintillator, and so we have more scattering where the electron will interact in the silicon and scatter out, and so you get only a partial energy deposition, which shows up as a bump on the lower end tail in the beta spectrum, which is shown on the lower plot where we have the 131M with the two conversion electron peaks, and then this kind of bump at the bottom, which makes it more challenging to do data analysis and pull out the signal. So I'm going to talk a little bit more about the noise problem and how we can resolve that. And the main way is to reduce the capacitance in the detector. And the approach that most people do is to go to segmentation or pixelization, so make the detector smaller, which reduces the capacitance and lowers the noise, and so you can get down to low noise. And so I'll be showing more of that as we go through. At PNNL, we've been working with a 16-strip commercial detector, and so we lower the capacitance in each of the strips compared to a monolithic detector. But this one is still a challenge. We're still having trouble with this. Showing here an example plot of an americium-241 source with a 59 keV peak. And you can see the noise peak coming up below channel 20, which is about 40 keV or so. And it turns out that we're not limited by the capacitance of the detector at this stage. It's really more about the data acquisition and data electronics, and we're working on the front-end electronics of this to reduce this noise. But you can see it's a challenge even in this segmented detector. Going to the other extreme, we can go to a highly pixelated detector. This is an example of a detector that has 50 15 micron size pixels, and so very small detectors. And they can be made to be very large size. This example is a 6 by 9 centimeter squared. These are being made by Lawrence Berkeley National Laboratory. And so very large area, 54 square centimeters. And they can be quite thick, up to 675 microns, which allows collection of the high energy betas in this silicon. And these are charge coupled devices, and so they basically, you collect a spectra for, or collect an image for a period of time and then read it out. This is an example of a 3 centimeter by 6 centimeter CCD with 8 megapixels. And so you collect the image and you get a lot of different interactions from the particles, and then you can use analysis methods to convert those images into energy spectra, which is what we normally use, and then analyze that. One interesting thing about the CCDs and these pixelated detectors is we get an image, and so we can start to look at the different interactions in the CCD, and you can actually do particle identification. So the different particles interact differently in these silicon detectors, and if you have an image and a way to process it, you can actually separate those out and lower your background. So I'm not going to go through all of these, but I just kind of give you an example of how these interactions are different. So if we look at the upper left-hand plot, where we have an alpha interacting, and the very top cartoon is where the alpha is interacting on the back side layer, and then the charge is drifting toward the front side where it is read out, and that produces a kind of typical round pattern with a large number of pixels that are hit with high energy. And then going around the different interactions, muons produce a nice straight line as they interact through the detector. Electrons tend to scatter around and produce squiggly lines, and then gammas or X-rays only interact typically one time in the silicon and then scatter out. And so they have a very small interaction with just a few pixels. And so by having these, and this is just a simplified version of it, but you can start to see how you might be able to detect the different and identify the different particles. So we have a system at P&L where we've been doing some testing. We found that these work better when they're cooled, so we operate these at 140 to 160 Kelvin. And so we put them in a vacuum chamber with a mechanical cooler to get them down to that temperature. And this is not, of course, a field system. This is just a laboratory system, but it's a nice setup. And here you can see a data acquisition from a combined 133 xenon and 131M xenon. And a couple of things to point out here. First, we have very low threshold on this. So the noise has been driven down very, very low to a few keV. And so we have this rich spectra that we don't normally see certainly a non-plastic scintillator. The other thing is that because we have very good resolution, we're operating these at a cooler temperature, we can start to get separation. We have very good resolution and see the differences in the conversion electrons and even in the X-rays, and be able to separate out the 131M from the 133. And so this is a very nice spectra. One thing I will point out is the conversion electrons have a tail on that. That's because of the dead layer on the CCD. And so we're now moving to what's called back-thin CCDs. So they basically have scraped off the back layer to provide the minimal amount of the dead layer. And so those will, they provide a much nicer resolution, although I don't have a picture of those right now. So a different approach is we're looking at room temperature pixelated detectors as well. This is a Timepix 3 silicon detector, which is developed at CERN. There's also the Metapix, but we're looking at Timepix. And each pixel is bonded to an ASIC readout, and so that allows you to have very low threshold, but operate at room temperature. And so we have very good timing resolution and the energy and XY position, and we can do the same particle identification. And this is just an example of different particle interactions in this detector. And so at PNL, we have been evaluating the Advocam silicon detector. It's a Timepix-based detector, but it's a commercial version of it. And we have a setup here that you can see with the piping where we can introduce gas and make measurements. And we have an example plots of two of these. The top one is the 131M. And you can see the two conversion electron peaks, and then also the 30 keV X-ray. The bottom shows 133, where we get the 30 keV, and you can actually see the 45 keV electron as well on the side, shoulder of that, and then the 80 keV peak. So we haven't done any particle identification or separation of the gammas from the betas at this point in time, but it really looks quite nice and shows a lot of promise. So we're running out of time, but just wanted to kind of talk a little bit about the work we're doing at PNL on these beta detectors, which we think as we go to segmented and pixelated will provide more capability, drive down that noise threshold so we have increased efficiency. And with the pixelated detectors allow us to do particle identification, which will even further drive down that background and provide more sensitivity for these types of systems. So I'll end here and be happy to take any questions.
Thank you, Dr. Reggie. There is any question?
Thank you, James, for a great presentation. The scattering of electrons in the silicon is something we've seen as well. Is there a solution to that? Is there something in the data that could be done, whether that's in coincidence mode or just by looking at the perhaps the pole shape analysis or something like that, that's different about the scattered electrons compared to the ones in the main conversion electron signal?
Yeah, that's an excellent question. We haven't looked in detail at that yet, but I think that there may be some opportunities. I'm not sure about the pole shape discrimination, but there may be some ways that we can help alleviate that. Of course, it's basically because of the Z of the material, and so you're always going to have scattering. If you kind of separate those out, which would help, I guess, but you're still losing the efficiency. So, yeah, I don't know the solution to that, but thank you for the question.
Okay, thank you very much, Dr. Reggie. Our last presentation today will be development of a new technique for 4P beta detection system to perform primary method for the measurement of activity of radionuclide, and will be presented by Dr. Heranudin from the National Research and Innovation Agency of Indonesia.
Okay, thank you for this opportunity. Good afternoon, everyone. I'm Heranudin from National Research and Innovation Agency of Indonesia. Today, I will present about development of a new technique of 4pi beta gamma detection system to perform primary methods for the measurement of activity of radionuclide. And this is the outlines of this presentation. As we know, that the accurate measurement of the radioactivity became extremely important in the early 20th century when scientists began to investigate the effect of radiation on living organisms. There are a number of fields that require accurate measurement of radionuclides, including nuclear medicine, environmental monitoring, and so on. The 4pi beta gamma coincident counting methods has been established as an obsolete method for radioactivity measurement for several decades. The offline analysis method has ability to extract and analyze valuable information from data that previously missed in the conventional real-time analysis. And this is the objective of this study. And this study starts from the basic principle of coincident counting. As we know, that the coincident counting method has proven to be a powerful technique for measuring radioactivity, and also to apply this technique, at least 2 independent detectors are required, each sensitive to one type radiation, and one detector must have 4-pi view of the source. In the beta decay, immediately followed by gamma emission, we assume A is the source of activity. And in the slide, we can see that the equation of the count rates of beta, gamma, and the coincident, while efficiency of detecting beta and gamma were formulated, as well as the activity. Then we use the correction and efficiency extrapolation technique. We use Smith formula to correct coincident counting data for the effects of non-extendable daytime and accidental coincidences. Utilizing a 4-pi beta detector, varying beta efficiency and extrapolating it to unit value can derive an accurate value of the activity. This method can be expressed as shown in the screen. Then we continue to development and setup of the system. We use plastic scintillator, in this case AJ212, as beta detector, and factory-made well-type sodium iodide scintillator as gamma detector. And we use the Gen 4 simulation to investigate the plastic scintillator that absorbs incoming electron while minimizing photon interference. The photon mostly come from gamma rays resulting from radionuclide decay and secondary Bremsstrahlung photon interaction with electrons. We use CAN N6751 10-bit digitizer to acquire signals from both beta and gamma channel, employing pulse-shape discrimination technique for signal identification. Several parameters such as duration of measurement, trigger threshold, and gate times were set before data acquisition. This is the picture of the diagram of the system in the top left. Upon exceeding the trigger threshold during the pre-gate time, the sample value is recorded as an event with a timestamp. Ensuring the correct charge parameter for each detector is crucial to obtain proper results. Upon completion of the measurement, the data is saved as binarily smooth files, with each file have 20 bytes information as shown in the table. So far, we can say that it is a highly effective means of data storage. Then, the recorded data can be analyzed without employing data acquisition hardware, thereby eliminating signal distortion caused by temperature and environmental condition. Python codes were developed to deconstruct the raw binary data. We also use Python program to conduct offline analysis method. The program independently applied non-extendable daytime to both the beta and gamma channels. It is also implemented a coincident counting methodology, only counted when a valid beta and gamma event occurred within a specified resolving time. Still in the offline analysis method, because we used cobalt-60 in this experiment, we applied 3 gamma window settings to the gamma channel. To vary the efficiency of beta detector, the lowest threshold of the beta gate, labeled as discriminator, is increased iteratively by number of channels. The highest threshold of beta gate was set at the maximum channel number of the beta spectrum. Algorithm of offline analysis method for calculating activity concentration of a source was developed also in the program. Then we continue to the source preparation. A required amount, about 0.5 milliliter of cobalt-60 solution, was drawn into the picnometer and dispensed on the plastic scintillator. Once dried, the scintillator with dropped source was glued to another blank plastic scintillator by BC600 optical cement. The plastic scintillator, which was wrapped by Teflon reflector tape, then placed directly onto the PMT surface. And then for the result, we got some results from the Gen4 simulation. The cobalt-60, for the cobalt-60, the 1 millimeter plastic scintillator is the optimum thickness for absorbing incoming electrons while minimizing photon interference at the same time. And also for beta detector, the simulated spectrum of the AG212 plastic scintillator corresponds closely to the measured spectrum of cobalt-60. The CompassCAN software presented a two-dimensional histogram of the beta-gamma channel for the source. In the scatter plot, we can clearly see the area with high energy corresponding to the main energy of beta in the left and the main energy of gamma in the right. As on spectra in the bottom, the developed Python program successfully implemented the time and coincidence algorithm for both beta and gamma channels. In the extrapolation, efficiency extrapolation was performed to obtain the final value of the activity concentration. The correction of background and decay were applied before the calculation of activity concentration. Setting variation of beta delay and resolving time can be addressed by the offline analysis. Only one set of experimental measurement data was used to find sensitivity of the efficiency extrapolation using several different settings of that time. The final result uptime was 150.9 plus minus 0.5 becquerel per milligram, agrees with the reference value of 155.4 plus minus 0.4 becquerel per milligram, to within one standard deviation. Several components are also taken into account to calculate the uncertainty budget. Conclusion. In summary, the offline analysis method for the coincident counting with 4-pi beta gamma instrument was implemented successfully. Using this technique, accurate calculation of absolute radioactivity measurement can be performed since the raw signals were first experimentally measured, without the need continually collect the data, reducing measurement time and unwanted data fluctuations. The offline analysis provide a level of flexibility that is not possible with real-time data processing. Researchers can easily adjust and refine their analysis technique based on their findings. This allows for more iterative and exploratory approach to data analysis, which can lead to new insight and discoveries. I think this is the end of my presentation. Thank you.
There is any question for Dr. Heranudin? Okay, I think that finished our three presentations for today. Thank you very much to the people, and thank you to the exposers.
If there's any questions to any of the presenters, we still have 5 minutes or so to. Yes, there is a question.
I have a question for Michael Foxe, if that's okay. Sorry, Michael, I missed some of your talk. I was eating a cake upstairs, it was nice. USL16, one of your slides was showing how changing the acquisition time changes the sensitivity to certain isotopes.
Yep.
What's the approach at your lab, USL16? How are you using different acquisition times, and if not, what do you use?
Right now, we just... So right now for USL16, we use the standard kind of 24-hour measurement time, which works well for the 133 and 131Ms kind of on average. But I think as we move forward, there's potential there if we want to try to target a different duration. But there's studies that I think need to also be done to understand what's the rate of the gas kind of loss from a cell potentially, or what's the impact on the longer measurement duration, so that we can certify those with the PTS as well.
If there are no more questions, then we want to thank all the presenters. Thank you very much for coming, and we close the session.
Thank you very much.